The topic is the first topic is atomic structure. Simply we can say as a structure of atom. Okay. Structure of atom. Structure of atom, or simply atomic structure. So in this one, what are the points we are going to discuss? In the structure of atom, the main important areas are Bohr's theory, de Broglie Heisenberg's theory, and quantum numbers are most important theories in this. Okay. First, coming into this, we know in any atom we are having more than 100 fundamental particles. Okay. Mm, As per Dalton's theory, atom is the smallest particle, which is invisible particle, which cannot be divisible. This point was explained by Dalton's atomic theory. Okay, and after that, experiments showed that in atom also divisible. Okay, that is can be into small particles like electron, proton, and neutron. It means in any atom, the major fundamental particles are electron, proton, and neutron. Okay. So after the discovery of electron, proton, neutron, the point is how these electron, proton, neutron are placed in the atom. Okay. For that one only, we are going to study the atomic models. Okay. Next concept is atomic models. So in the atomic models, okay, in the atomic models, we are going to discuss first one. Which atomic model we are going to discuss? Thomson model. We are having Thomson model, Rutherford's model, as well as Bohr's model. We are having. First one is uh, Thomson model. Thomson model. Okay. This Thomson model is, so what he considered generally. So at the time of Thomson model and Rutherford model, neutrons were not discovered. Okay. Neutron model was not sorry, neutrons were not discovered at that time. So in the Thomson model, what he said that atom is considered as a positive sphere. Positive. Okay, plus V means positive sphere in which electrons are embedded in such a way that the electrons are embedded in such a way that okay, that the atom gets electrically neutral. That means, for example, if I'm taking this, so this is the atom of a positive sphere. Okay, this is the positive sphere. When by considering it is a positive sphere, so positive sphere means what we can say that all the protons are arranged or aggregated in a spherical manner. In that one, what we can say, the electrons are embedded like this. Okay, it is not having any specific or any specific direction or anything is not there. Just electrons are embedded so that how much positive charge is there. So in the same amount of negative charge will also be there. So that what we can say the electron should be electrically neutral. Okay, in Thomson model also we are having, that's why this model is also known as, this model is also called plum pudding model, plum pudding model, or watermelon model we can say. Watermelon model we can say. Okay, this is about the uh, Thomson model, and this Thomson model also failed to explain why the atom is stable and how the atom is getting stabilized. Okay, so in order to explain this, so Rutherford's came into the picture. That is only we are saying that Rutherford alpha scattering experiment. Rutherford alpha scattering experiment. Rutherford's alpha scattering experiment. So, what is Rutherford's alpha scattering experiment? Okay, so for this one, Rutherford alpha scattering experiment, for Rutherford alpha scattering experiment, first he considered a source of alpha particles. First, he took a thin gold foil he has considered. Okay, why the gold foil it is considered? Because of its high malleability and ductility. High malleability and ductility. So malleability and ductility means what we can say, simple having which can be converted into wires and which can be converted into sheets. Now this is considered as the atom, okay, or matter. So around this matter, what he considered, what he put, he has used a fluorescent screen. He has used, okay, likewise a fluorescent screen he has used. This fluorescent screen is made up of zinc sulfide. Zinc sulfide. The name is zinc sulfide. PHID. In that one, Za oxidation state is +2 and sulfide oxidation state is -2. Okay. The zinc sulfide screen, how it will act as? It will act as a fluorescent screen. SCENT, fluorescent screen. Fluorescent screen means what we can say, whenever light strikes on this screen, a tiny flash is going to observe. Okay, whenever light strikes on the surface, no, so a tiny flash is going to observe. Okay, the tiny flash only, where from that only we can identify. Now what he is taking, uh, he is taking one slit, and before that one he is taking one source of alpha particles. This is what source of alpha particle. Okay, when the alpha particles are passes through, okay, these are the alpha particles are passes through the foil. So when this is observed, when the alpha particles are passes through, no, he observed most of the alpha particles are passes through the foil. Likewise, that how, that means most wherever the light is striking on the surface, okay, wherever the light striking on the surface, we are going to get a tiny flash we are going to observe. And some of the particles are some of the particles or some of the alpha rays are deflected with small angles like this, and very few particles are bouncing back like this. Okay, so mainly what in this experiment, what he has taken a gold foil, and around that gold foil, he observed a fluorescent screen. From the fluorescent screen only, what he observed, this will act as a j- whenever a light strikes on the surface, it will get light tiny flash is going to observe. Now, when the source of alpha particles means what? Helium 24, helium 2 and with atomic mass 4 is only known as alpha particles. When these alpha particles are passes through the met gold, then what we can observe, most of the alpha particles are passes through, and few are bouncing back with small angles, and very few are reflecting back. Okay, very few are reflected back or bouncing back, we can say. Very few are bouncing back. So how we are going to get this, we are going to see here. Students, can you understand what I'm trying to say?
Yes, sir.
Okay, okay, thank you. Now see, so from the observations, he made three observations. Okay, from the observations, the conclusions are, mm, so what we can say, as most of the alpha particles are passes through, then what we have said, in an atom, in atom most of the space is hollow. Hollow means what we can say, simply empty. Okay, empty, not THY, it is TY, right? Next one, what we can say, and one more thing, he said, as the very few particles are bouncing back, that means what? These alpha particles are positively charged particles actually. Okay, positively charged particles. When the positively charged particles are striking or hitting at the positive charge, then for example, say this is positively charged particle, and this wise electrons are like light is hitting. So when light is hitting, then immediately what will happen? It will come back, no? Because this is also positively charged and this is also positively charged only. So automatically repulsions will be there likewise. And next one, what we can say, uh, positive charges concentrated at the middle of atom. Okay, that concentrated part only, middle of atom, in a small region, in a region small region called nucleus. Okay, so he was the first person who described about the nucleus. Next point is, okay, next point is, uh, so around the nucleus, around the nucleus, electrons will revolve, electrons will revolve, sorry, uh, electrons will revolve around the nucleus around the nucleus, how planets how planets revolve around the sun. Okay, how planets will revolve around the sun. So that's the reason this model is known as okay. That's why this model is also called as. That means he was not able to explain this electrons will revolve in a circular manner or a elliptical manner or any other manner. It was not explained. Just he explained how planets will revolve around the sun. In the same way, electrons will also revolve around the sun. That's it. Next one, electrons will revolve around the nucleus. How planets will revolve around the sun. That's why this model is also called as. This model is called planetary model. Planetary model. Okay. Hmm. This is the uh, Rutherford's alpha scattering experiment. So in this one also certain limitations are there. Okay, that limitation we are saying that drawbacks, certain drawbacks are there from this theory. So in this one, what is the first major drawback is? So how the atom is getting stable, that was not explained. Okay, the major drawback is, for example, if according to classical law of physics, for example, if any particle is, let me take this as, okay, this is the center. Okay, around the center with certain distance some r, the particle is rotating like this, whether it can be circular motion or anything. Okay, when it is rotating, the particle should lose its energy, and finally it will gradually lose its energy and it will come nearer to the nucleus and finally should fall into the nucleus. So if it is happening so, then atom should get a collapse, but it is not actually happening. Why? That is also not explained by theory. That means that only we are going to discuss under classical law of physics. Okay, that is according to classical law of physics, classical laws of physics. If a particle is revolving around a center with a particular radius, it should lose it should lose its energy continuously and finally fall into the nucleus. Finally fall into the nucleus. Okay, if this is true, okay, then they finally enter the nucleus and then atom should get collapse. Atom should get collapse. Okay, but it is not happening. Why this is not happening? So how atom is stable, that was also not explained by this theory. So in order to explain this theory only, okay, Bohr came into picture and he prescribed his own theory. So before discussing about this theory, we need to know, before Bohr's theory, what are the developments made Okay, what are the developments made? What are the developments made in science, and what are the developments we need to discuss? Okay, students. Mm. That is only next we will discuss about the wave theory and Planck quantum theory. Wave theory and Planck quantum theory we are going to discuss. That is wave theory. Wave theory, which is proposed by uh, okay, this theory was proposed by James Clerk Maxwell. So he's saying that the energy which is emitting from any source, okay, the energy which is emitting from any source, like a light or incandescent lamp or any tube light or anything, it will come continuously in the form of radiations. Okay, that energy only we are saying that the energy associated with the radius only we are saying that radiant energy. That means what? He is saying that the energy emitted from any source, it can be light or heat, anything. Okay, the energy emitted from any source, like like lamp, tube light, like light or incandescent lamp, incandescent bulb, incandescent bulb. Okay. Like the energy emitted from any source like light or in case of emitted in the form of any source in the form of in in bulb continuously in the form of radiations. Okay, in the form of radiation, that means the energy which are we are going to get now, that all comes in the form of radiations only. Okay, uh, and the energy and the energy associated with radiation is only known as is called radiant energy. Radiant energy. Okay, the energy continuously in the form of radiation is only called radiant energy, we can say, right? Radiant energy, we can say. When this energy is coming, no, when these radiations are coming down, for example, let me take this is like propagation. That means direction of the wave. That is, we can say simply propagation of the direction. Propagation of the direction. That means in this direction, the radiation should come. Let me take this is like a source I'm taking. Okay, let me assume this is source. So when a radiation is coming from any source, no, it will come continuously in the form of waves like this. Okay. So while these radiations are coming, no, while it is coming, okay, these radiations, it will produce two types of fields. That is what, let me take this is electric field, and one more we are going to get like this. in a perpendicular to this. This is magnetic field. That means when the radiations are coming down, okay, when the radiations are coming down, these will create two types of fields. Okay, these radiations, these radiations, these radiations produce oscillating electric and magnetic field. Oscillating electric and magnetic field. So these two will produce two fields like electric and magnetic field, which are perpendicular to each other and perpendicular to the propagation of the wave. To the propagation of wave. Okay, that means what we can say, both waves, electromagnetic radiations are perpendicular to each other, that both field, and as well as see, this electric field and magnetic field are perpendicular to each other, as well as this is the direction, right? So this direction also perpendicular. That's the why these radiations only called. That's why these radiations are called. These radiations are called. These radiations are called electromagnetic radiations. Electromagnetic radiations. Okay. That means, and these radiations. Okay. These electromagnetic radiations EMR I'm going to represent. Okay, electromagnetic radiations I'm representing as well. How? EMR. These electromagnetic radiations doesn't require any medium for the propagation. Medium for the propagation. That means for the propagation, it doesn't require any medium like water or anything. Just like sound. Okay. Next one. These radiations travel with a velocity of light. These radiations travel with the velocity of light. Velocity of light. That means simply what we can say. These radiations are there, no? These radiations, simply, if I want to say simply, the electro or the light which is emitting from any source, no, it will come in the form of waves by continuously making it waves like this. Okay, likewise we are going to get. In the form of waves we are going to get in a continuous manner. This is the point you need to remember. Just like it is like how ordinary, like this is light wave, we can say light wave. So what are the wave characteristics of a normal sound is there? So in the same way, this light wave also have same characteristics of a sound. That is only next we are going to discuss. That is wave characteristics. Wave characteristics. Okay, that is only we are saying that wave characteristics. So this wave characteristics, what we can say simply, in the wave characteristics, first one, amplitude. Amplitude means what? This is height, or this is depth. This is known as a crest, and this is known as trough. Trough. So amplitude means what? It is the height of the crest, or depth of the trough. Okay. Generally, units, what we can say, units are okay, just length units only. General length we will measure in terms of centimeters or meters, no? Centimeters, meters. Likewise, we can represent. And next one is wavelength. Okay, next one is what? Wavelength. So the wavelength means what we can say. Wavelength means uh, it is the distance between two successive crest are true. Okay, this is only we are saying that, like, these are the two successive crest, no? Between this distance is there, no? That is only known as lambda, or this also we can say as a lambda. This is represented as a with lambda. We will pronounce as LAMBDA, lambda. Okay, and the units are angstrom, angstrom, that is E naught. Angstrom units are nanometers, nanometer nm, or picometer pm, picometer pm. Okay, generally one angstrom unit is equal to 10 to the power of minus 8 centimeters, and r, which is equal to 10 to the power of minus 6 meters. Sorry, minus 10 meters, no? And 1 nanometer equal to 10 to the power of minus 9 meters, or 10 to the power of minus 7 centimeters. You need to remember, so that we can use it for solving the questions. And picometer. 1 picometer equal to 10 to the power of minus 12 meters, or 10 to the power of minus 10 centimeters. Okay, you need to remember this. Okay, na? Need to remember. Remember this while solving the questions. Okay, next one. Next one is wavelength. No, next one wave number. Okay, wave number means it is like a reciprocal of it is wave number we will represent with nu bar. It is a reciprocal of wavelength. Wavelength. That is nu bar, wave number nu bar equal to 1 by lambda. Okay, therefore what we can say, units are centimeter inverse or meter inverse. As we are saying, lambda is angstrom or nanometer or picometer, no, that all in centimeters only, no. That's the reason it can be centimeter inverse. Or next one, wavelength wave number. Next one, frequency. Next parameter is frequency. Frequency. Frequency means the number of waves passes through a point per second. The number of waves passes through a point per second. And we have frequency we are going to represent by, it is represented by nu, like we will pronounce it as a nu, nu. Okay, and units are cycles per second, or simply second inverse, or hertz, hertz. Simply we represent hertz. Okay, hertz we can represent. And next one is velocity of a wave. Velocity means what? It is linear distance traveled by a wave. Velocity means what? Linear distance traveled by a wave. It is linear distance traveled by a wave. Okay, velocity units you know, like light velocity. So from there, he had given one relation also, that is the relationship between important formulas. Okay, the relationship between velocity, frequency and wavelength. Frequency and wavelength. That is C equal to nu lambda. Okay, C equal to nu lambda. This is the point. So as we are having, okay, uh, each and every electromagnetic radiations with a different wavelength. If all the electromagnetic wavelengths are arranged in a sequence, then the spectrum which we are going to observe is known as electromagnetic spectrum, we can say. Okay, the spectrum which we are observe is known as a electromagnetic spectrum, we can say, right? That means what is the next point is uh, all the electromagnetic radiations, electromagnetic radiations, radiations are arranged in the order of their wave, increasing their wavelength in the order of increase in wavelength, increasing wavelength or decreasing frequency, wavelength or decreasing frequency. The obtained spectrum is called, the obtained spectrum only called, is called, spectrum is called electromagnetic spectrum. Electromagnetic spectrum. That sequence we need to remember, that is CGX This is in the order of their lambdas, and this is in this order. It will be their frequencies. C represents cosmic rays. Cosmic rays. This represents gamma rays. Gamma rays. X represents X rays. U represents ultraviolet rays. Ultraviolet rays. V represents visible region. IR represent infrared. Infrared rays. M represents microwaves, and R represents radio waves. Okay, so these are the cosmic and all the electromagnetic radiations which we are going to observe in the this. Okay, so this is about the wave theory and their conditions, and from the electromagnetic spectrum and relationship between the points. Am I clear, students? I hope you all understood. I believe, right? Any doubts? If you have any doubts, no, please ask me. Okay, so then we can close for today. Okay, we can close for today, and we will meet in next class. Bye, students. And notes I will share to sir. Sir will share in your respective groups. Thank you, all of you. Good night.